All right, this is where we left off. We still have 3 more situations to talk about. These are general situations. I'm giving you a graph of a parabola here. I'm giving you sort of a graph of a cubic looking function here. But the idea is not that it's a parabola. The idea is not that it is a cubic function. The idea is that it is a U and a snake. Okay? What sorts of polynomials make U shapes? Even degree polynomials. What sorts of polynomials make snake shapes? Odd degree polynomials. Okay? So we did this one here. Let's go ahead and do the one that's similar to it below. What is the degree of this polynomial? Even. I don't know if it's 2 or 4 or 6. I just know that it's even. The leading coefficient here must be negative because this graph has been flipped. So the leading coefficient, I don't know what the actual number is, but I do know its sign. Its sign is negative. End behavior. Remember, end behavior is what does the graph do as x goes to positive infinity or as x goes to negative infinity. Well, as x goes to positive infinity here, what does my graph do? Goes down. As x goes to negative infinity, what does my graph do? Also goes down. So I'm going down to down. So I write down to down. If you wanted to be more formal about that, you could write this. As x goes to positive infinity, comma, f of x, the function itself, goes to, the graph goes down for forever, so that's going to negative infinity. So you could write negative infinity. As x goes to positive infinity, the function, the graph, goes to negative infinity. Okay? Up here, as x goes to positive infinity, the function or the graph goes to positive infinity. That's the formal way of saying up to up, down to down. Okay? Turning points, do we have any? This is where the graph switches from increasing to decreasing or from decreasing to increasing, and we do have one. There's one sitting right there. We haven't talked about how to calculate turning points yet, but we will. Okay, is there any interval on which the function is increasing? So we are increasing here, right? You read the graph like a book from left to right, and then you're just looking for where the graph is rising. The graph is rising from all the way down here up to here. So the interval that the graph is increasing would be parentheses, negative infinity, comma, 0, parentheses. Meaning x is less than 0. And on this particular graph, do we have any decreasing areas? Yeah, all this stuff here. So starting at 0 and going for forever. So decreasing, starting at 0, not including 0, going for forever. Can't include forever. So from 0 to infinity. It's not negative infinity because we're talking about what values of x are decreasing. And the values of x are these guys here. Okay? So this would be x is greater than 0. Values of x that are greater than 0, the function is decreasing. Values of x that are less than 0, the function is increasing. The graph is rising from left to right. Or the graph is falling from left to right. Okay? The important thing here, though, is this. The degree, the leading coefficient, and the end behavior. The degree, the leading coefficient, and the end behavior. If it's an even degree polynomial, it'll form a U. If the U is upright, the leading coefficient must be positive. And the end behavior will be up to up. If it's an even degree polynomial, the leading coefficient is negative, then that U is upside down. And the end behavior will be down to down. So again, the focus on these two is not necessarily the increasing or decreasing part. The increasing or decreasing on this one and the turning points are just examples of what we're looking at. The important thing here is the degree, the leading coefficient, and the end behavior. All right? That is what you have to get out of this. So what's the degree of this polynomial going to be? Odd. It looks like a snake. So it must be an odd degree polynomial. The leading coefficient in this case is going to be positive. If you think of a line, A line going up from left to right has a positive slope. A line is an odd degree polynomial. Same thing is going to be true here. This one kind of goes up from left to right overall. This is a positive leading coefficient. What's the end behavior here? Okay, so it starts out low and ends high. So as x goes to negative infinity, this thing goes, as x goes to negative infinity, this graph goes down. As x goes to positive infinity, this graph goes up. So we're going to write down to up. It starts out down, it ends up up. Starts off low, ends up high, okay? It's down to up. It starts out down and goes to up. If I want to be more formal with the way I wrote that, then I would have to write as x goes to negative infinity, f of x goes to negative infinity. As x goes to positive infinity, f of x goes to positive infinity. Which would you prefer? Both of those, right? This is end behavior, this is end behavior. Which one would you prefer to write? Down to up, or as x goes to negative infinity, f of x goes to negative infinity, as x goes to infinity, f of x goes to infinity. Down to up, okay? So this is what I want to see, but this means this. As x goes to negative infinity, so that's this way. As x goes forever this way, what does my graph do? It goes to negative infinity, this way. As x goes to positive infinity for forever, what does my graph do? It takes off and goes to positive infinity, like in the y direction. Okay, so that's what all of that right there means. Just writing down to up takes care of all that for you. It's easier. It's faster. Makes more sense to most people. Do we have any turning points here? No, actually we don't. We're increasing, and we're still increasing. So we never turned around. So there are none on this one. On this one, it doesn't mean that in an odd degree polynomial there won't be any. On this particular one, there are none. What intervals are we increasing on in this particular example? Are we increasing in this region here? Yes, because as we read it from left to right, the graph is rising. Like if we were a dot moving along, we would be going up. What about in this region? Are we increasing here? Yeah. We're rising the whole time in this particular graph. So we're actually increasing always. Are we decreasing ever? Nope. So never here. In this particular example, okay? Again, I need you to know this. This is true for all odd polynomials. These guys here are true for this particular example that we're looking at. This is what you need to know. This is always true. Finally, the last one, this graph. What degree polynomial are we looking at? Odd, again, because it looks like a snake. What's my leading coefficient here? It's negative because this graph is going down from left to right. Just like a line going down from left to right has a negative slope, this has a negative leading coefficient. End behavior in this case? Up to down. So up to down. Just start on the left. Where's the graph at? Up or down? Up. Go to the right. Where's the graph at? Up or down? Down. So you write up to down. Do we have any turning points on this one? No. Are we ever increasing? No. Are we ever decreasing? Yeah. When? Always. Okay. So in this particular case, that would be your answers here. But what you need to know are these three things. Okay. So look at what I have circled here. We have the degree, leading coefficient, and behavior for all three. If the degree is even, the graph will look like what? The degree is even, the graph looks like a U. If the degree is odd, the graph looks like a snake. If the degree is even and the leading coefficient is positive, the U will be right side up or upside down. Right side up. If the leading coefficient is negative, the U will be upside down. If the leading coefficient in an odd polynomial is positive, the graph will go From left to right, the graph will start off low and end high. It'll go down to up. It'll do some stuff in between. Like on this one, it's doing some stuff in between, but it starts low and ends high. Down to up. If the degree is odd and the leading coefficient is negative, that reverses. We start off high and we end low. We do some stuff in the middle, but the overall result is up to down. These are the three things you need to get out of this page right here. There's lots of information here, but I need you guys to know those three things. Okay, I have some examples here of graphs that are polynomials, and I want you to tell me the end behavior, tell me if it's an odd degree or even degree function, and then tell me if there's turning points, and tell me where it's increasing or decreasing, okay? Now, we don't have actual numbers on this graph, and I don't have the actual equation, so we're just going to basically point out where we're increasing and where we're decreasing, like labeling increasing and decreasing, okay? So first of all, what degree polynomial do we have here? This one's odd. We don't know if it's a 3 or a 5 or a 7. All we can say is that it's odd because it looks like a snake. We need to describe end behavior. What's end behavior here? Down to up. Okay, describe end behavior. We did. Odd or even, we did. State turning points. Do we have any turning points here? There's one here, and there's one here. Okay, I'm just going to circle them. And you can label them on your notes, call them turning points. And the intervals where the function is increasing or decreasing. Do we have any increasing areas? Where? Here? Is that increasing? Yes, this is increasing. Is this region increasing? No, this one is decreasing. And next, is this one increasing? Yes, so I'm going to write increasing here. Okay? That's all I'm looking for on problems like that. In a little bit, we'll figure out how to determine where those turning points are and the intervals, the actual intervals, where they're increasing and decreasing. Okay, next one. Degree here is, does it look like a U? It's odd. We can't say for sure, but from what we see, we can tell that it's odd. That's all we can say. Okay? It does look like a line, which would make it a 1 degree polynomial, but we don't know for sure. So it's an odd degree polynomial. End behavior is up to down. Do we have any turning points? No. Do we have any intervals where the function is increasing? No. Do we have any intervals where the function is decreasing? Yeah, the whole thing. So I'm going to write decreasing right there. The whole thing is decreasing the whole time. And the last one. The degree here has to be even. Why? Yep, we see a U shape. End behavior? Up to up. Do we have any turning points? 3 of them. We turn around here, we turn around here, we turn around here. Do we have any intervals where we are increasing? How many? 2. Where are they? So, all right, so we got chunk 1, 2, 3, 4. Which interval is increasing? So this one's increasing, and this one is increasing. That's right. Which makes the other 2 decreasing. If you see the graph going down from left to right, it's decreasing. If you see the graph going up from left to right, it's increasing. If the graph turns around, that turning point is neither increasing nor decreasing. For these next 3 problems, the directions say describe the end behavior of the following functions. We're going to do that, but then we're also going to see on the graph, when we graph it on our calculator, which we're not doing right now, don't do it right now. Put your calculator down. Down. Let it go. Thank you. Oh yeah, I'm sure. So we're going to describe end behavior first, but then we're going to graph it to check to make sure that we are correct. And then once we do that, we are going to find turning points and intervals of increasing or decreasing. So let's add that on here. And turning points and intervals of increasing and decreasing. And turning points and intervals of increasing or decreasing. So without graphing now, look at that first polynomial. Ask yourself, what is the degree of that polynomial? So it's odd. What is the leading coefficient? Positive. We have an odd positive polynomial. So what's the end behavior going to be? Down to up. For the second one, what is the degree? So I see 4, so that makes it even, which means my graph will look like a U. And what is the leading coefficient? Negative. So that makes this U upside down. So what's the end behavior going to be? Down to down. So it's on the ACT. Nice. Okay, try to do the last one on your own. Don't say. So first of all, the degree is 3, which makes it odd. So our graph will look like a snake. Now we just got to figure out which way the snake is going. The leading coefficient is negative. So therefore that snake is doing this, which means we are up to down. Okay? That is how you do end behavior. All you need is the degree and the leading coefficient, and you have a pretty good idea of what the graph looks like. On this one, it's a 4th degree polynomial that's upside down. I know it's going to look like a U. I know because it's 4th degree, it could have some sort of little bump in the middle, so the graph probably looks something like this. I don't know exactly where it is, but I know it kind of looks like that. And this first one, 4x to the third minus 3x, again, it's a cubic, it's odd, its end behavior is down to up, so I know it's probably going to do something like that. Okay? That's as far as you guys have gotten as far as understanding what the graph looks like, but you're already farther along than you were before you started this section. Before you started this section, you probably had no idea what the graph was ever going to look like, and you would have to plot points or use your calculator. But now just by looking at the equation, I can already picture what this thing's supposed to look like. Okay? So now we're going to actually go to our calculator, and I want you to bring up the graph and enter that in. So, go to the graph, and I want to enter in 4x to the third minus 3x. Don't forget to exit out of your exponent once you enter in that to the third power, and then subtract, not negative sign, 3x. Hit enter. And there's your graph. Notice that it does look similar to the sketch that I drew here. It was just a sketch, but I have it reasonably accurate. Okay? Is its end behavior down to up? Yes. Now I need to talk about what I wrote down here. Turning points and intervals of increasing or decreasing. I want to actually calculate the turning points. So I got to figure out where this thing turns around. To do that, I'm going to press menu, and I usually analyze the graph when I'm trying to do something. Which one of these options seems like the best option for what I'm trying to do? Maximum. That's right. It's not overall maximum, but in that little region right there, it is a little maximum. It's called a relative maximum. So I'm going to choose maximum, option 3 on my calculator. I have lower bound, so I just need to be to the left side of what I think a maximum value is. Slide across to get the actual ordered pair. For me, I have to move this, so I'm going to click and hold until it moves. If it'll let me, probably won't let me because I'm on a... Okay, let me try it on the mouse. Grab it. Okay, here we go. So I have my ordered pair of negative 0.5, comma 1. That's a turning point. So if I was asked for turning points, I would write down that ordered pair, negative 0.5, comma 1. I have another turning point over here, this low point right here. So I want to menu analyze again. What am I looking for this time? Yeah, minimum. It's not the overall minimum, but locally in that little area right there, it is a minimum. So I'm going to call it minimum. And then in lower bound, left side of that minimum. Upper bound, right side of that minimum. And it gives me that as an ordered pair. So 0.5 comma negative 1. So if the problem asked me to come up with the turning points, here they are. Negative 0.5 comma 1 and positive 0.5 comma negative 1. Those are the answers for the turning points. We'll write these down. We have turning points. One of them was negative 0.5, which by the way is negative 1/2, so you could write negative 1/2. So negative 0.5 comma 1, and then my other one was positive 0.5 comma negative 1. It also asked us, or I also asked you, to tell me the intervals of increasing and decreasing. So now that I have numbers sitting here, I have x coordinates, I can write those intervals out using interval notation. So I'm going to do that. We are increasing. If you remember the graph, oops, wrong one. If you remember the graph, we're increasing from negative infinity all the way to that x coordinate, which is negative 0.5. So let me make this always stay. Increasing from negative infinity to negative 0.5. And we're also increasing, so and. We start increasing here again, which was at 0.5, so 0.5 to infinity. We're decreasing, I don't have room, so I'm sorry I'm writing this all over the place, but we're decreasing where? Exactly. From negative 1/2, from here to positive 1/2. So from negative 0.5 to 0.5. And I know that notation looks like an ordered pair, and that's an unfortunate side effect of interval notation, but we just got to understand that that's not an ordered pair. That's an interval of values of x. All the x values between negative 0.5 and positive 0.5 were decreasing. All of the x values outside of negative 0.5 and outside of positive 0.5 were increasing. And that's what this notation right here is saying. So on your homework, when you are asked to do this, this is what they're asking you to do. Okay? Use maximum and minimum to analyze and get those ordered pairs. And once you have them, set up your intervals and interval notation. Make your answers match what the book has. All right, so I've changed to the second equation here. And you can see that my sketch of the graph, I knew it was going to be an upside down U shape with a bump in it. And sure enough, it's an upside down U shape with a bump in it. Okay? Now because I changed my original function to this function, it actually gave me one of my turning points already. It says negative 5.03 e minus 8. What does that mean? Negative 5.03 e minus 8. The e minus 8 is scientific notation. That's like times 10 to the negative 8th power. Times 10 to the negative 8th power is a very, very small number. If I were to write that out, I'd have to move the decimal over 8 places to the right. So 0.000000503. And it happens to be negative. Is that a big number? No. It is incredibly small. When you're using a graphing calculator and it gives you a number that looks like this, take a look at that number. It's actually an incredibly small number. The calculator screws up from time to time, and it will give you an answer like this when it means to say what? What number is that actually? Negative 0.000000053. What number is that pretty close to? 0. Yeah. The calculator, when it calculates things, sometimes has a little bit of leftover stuff, and it doesn't know what to do with it, so it shows it to you. This is actually a little mistake that the calculator does. That should say 0. Okay? So this ordered pair right here should say 0, comma 2 as a turning point. So I'll write 0, comma 2. Yeah, so if I have 3 of them, then this one, I'll use the calculator and ask it to find a, what? Minimum. And I use the calculator and ask it to find a maximum. Okay? Once you have those 3 ordered pairs, you have your 3 turning points. And then you have the numbers that you need to set up your intervals. Okay? So then we'll be increasing from negative infinity to 0. We'll be decreasing from 0 to, looks like 1. We'll be increasing from 1 to, looks like 2. And then we'll be decreasing again from 2 to negative infinity. Or, sorry, to positive infinity, as x goes to positive infinity. Okay? Do I need to show you how to do that too? Or are we good? We good? Okay. In this particular problem, the turning points worked out to be exactly whole numbers. They won't always be exactly whole numbers. You might get a really bizarre, like 0.185 or something. Just a weird number, okay? Whatever the calculator gives you is going to be your answer, except for when it gives you something wacky like that. Then you got to think, okay, that's actually 0, okay? Okay, graphing cubic functions by hand. Kind of a bummer. We have calculators that'll do it for us, but we want to learn how to do this by hand. To do it, set up a table of values, choose easy numbers, and generate ordered pairs. And then probably the most important thing on this page is what? You may need to choose decimals to get a good graph. Okay? So for this 1/2 x to the third, let's set up a table of values. Let's go x and y. I should choose some negatives and some positives. So I'll go -3, -2, -1, 0, 1, 2, 3. And if I need to, I'll pick some decimals. Actually, you know what? Let's scratch that. I'm going to erase these, and I'm going to go straight to picking decimals. -3, -2.5, -2, -1.5, -1, -0.5, 0, +0.5, 1, 1.5, 2, 2.5, 3. Now we're going to come up with a table of values. So we got to plug all those numbers in to our equation and simplify them down, and then we've got a table of values, and then we'll be able to plot points. Sound like fun? No. We're also going to apply what we've already learned. What is the degree of this polynomial? So what will its graph look like? Look like a snake that goes down to up. So we know we're going to start down here somewhere, and we know that we're going to end up here somewhere. Okay? So we know the end behavior. We just got to figure out what's going on in between. What I'm going to tell you is once you get end behavior on both sides, you're done. You just need to graph enough points in between to show what's going on in between. But once you get into end behavior, which means once I get into big numbers, big negative numbers or big positive numbers, then I'm in end behavior and I'm done. Okay? The other thing I'm going to tell you is don't do this by hand because it's terrible. What you were going to do instead is use your calculator, not to make the graph, but to get the points. So on your calculator, you need to, let's get rid of this function here. So, get rid of the function. And let's go ahead and enter in 1/2 x to the third. Okay, there's my function. I don't need that ordered pair. I'll just move it off to the side. because I just changed my function and it's still giving me those ordered pairs. I don't need them. Don't worry about it. Okay, press menu, and we want to, oops, I don't know what just happened there. We want to view a table. So we're going to go to table and split screen table for me. For you guys on your calculators, I think it says view table. It's like option 5 or something. So from here, what you're going to do is press menu. As long as you're on the table side, and you're going to go with, I believe it's, for me it's option 2. Yeah, you want edit table settings. For you guys, you're going to go to table, so press menu and then table, and then edit table settings is option 5. And you'll see this window come up. Table start. I want my table to start where I was writing down my numbers. I started my table at -3, so let's start this table at -3. So type in -3. Go down to the next one. Table step means how much am I changing each time? For us, how much are we changing each time? 0.5. So I'm going to type in 0.5. Don't worry about independent and dependent. Just go down and press OK. And the table will change. There's my -3. So I write down all these values in my table. -3 is -13.5. And I need to check that box again. -2.5 is -7.8. -2 is -4. -1.5 is -1.6. Looks like 8, so maybe 1.7. On your graphs, you're not going to be that accurate, so you don't need to worry about all these decimal places that you're getting. So I scroll down a little bit. -1, I have -0.5. At 0, apparently 0 disappeared on me, I have -0.06.
What if your like 0.5s and stuff are like way too small?
It's fine. You just want to copy this table down. So -0.06, and then at 0 I have 0. And then I keep going. Something crazy just happened here. Then I have positive 0.6. For 1 I have positive 0.5. For 1.5 I have 1.7. For 2 I have 4. I still haven't hit end behavior yet. I don't have huge numbers. For 2.5 I have 7.8. For 3 I have 13.5. And now I'm getting into big numbers. So that's all I need. Plot all those points. I know the bell's going to ring here in a second, but just bear with me. So we're going to plot all those points, and we will wind up with that graph. Then we draw in that graph, and we're done. Okay? Don't do these by hand. Use a calculator. It makes your life a lot easier.